In the previous video, we learned about the thumbs up rule and the cover up method. Now we're going to learn about partial fraction decomposition where the denominators contain factors that have complex roots. Let's get right into it. Alright, as we are done with the cover up method of calculating partial fractions, now we move on to another method. And alright, so first of all, let's without defining the type, let's look at an example and then define the type. That would be easier. All right. So let's say we have a function of y, function of s, like this. This is the form of the function s. So what we can do is that this one, there is no partial fractioning it. This is already partial fractioned. We can't break it even further. But for the first expression, we need to break it even further. Like for the first expression, we can write it like this, right? We can break up the whole squared part and we can write it right like this. And then we can just do that, right? So this is the first part of ys actually. So I wouldn't say it that this is the ys. Okay, so we need to convert this and we need to break it into partial fractions. Okay, the second part of this expression, we are not going to do that. This is already this is already broken into its smallest form. We cannot break it even further, but the first expression, we need to break it into partial fraction, and then we need to determine what will be the coefficients be. Now, let's look at the denominator to define its type. So in the denominator, we are seeing there are two algebraic expressions like this. All right, so if we try with your calculator, I want you to try to find out what their roots are. All right, for the first one, the roots are these two. And for the second one, the roots are these two. All right, that's what I was talking about. See, in the first type, the thumbs up rule, we had linear roots, s plus 1, s minus 2, s minus 3, or a type reducible to linear factors. In the second part, we had repeated roots, but still they are in linear factors. But here, the denominator is in such a type that there are imaginary roots coming out of our denominator factors. And if there are imaginary roots coming out of the denominator factors, then we're going to use another rule. So there are two ways of doing this. Okay. First of all, this denominator has another thing in common. Like these, the first part of both of the two denominator factors are the same, s squared plus twice s. So this is another special characteristic among them. First of all, they are both equations that result in complex roots. And the second part is the first two expressions of both of the factors are the same, which is s squared plus twice s. So we can use that. Actually, we can use that to our advantage, and we can actually convert them. We can say that s squared plus twice s, let s squared plus twice s equals to z. We can actually do that. So if we do that, what does the expression become? It becomes z plus 5 times z plus 2. So now we're going to be easily able to convert this into two partial fractions. It's just a thumbs up rule, right? I hope you understood it. The process is what? First of all, we looked at the denominator and we found out that the factors in the denominator contained complex roots. That's one thing. And the another thing that we noticed about the denominator factors is that the first two expressions of both the factors are the same. So if we assume that the first two factors, like s squared plus twice s, is equals to z, then we get a simplified factor like this. And with that simplified factor, we can easily convert it into partial fractions using the thumbs up rule. So now this has become a simple case of using the thumbs up rule, right? I won't be doing the maths. I hope that you will be able to find it. The answers I will write. So these are the answers. And this math is going to be your homework. So what are the answers? What do the answers tell us? The answers tell us that this is going to be negative 1 by 3 times z plus 5 plus 1 by 3 times z plus 2. All right, now if we substitute z, the actual value of z, s squared plus twice s plus 5 plus 1/3 s squared plus twice s plus 2. And so the whole expression of ys, what would it become? The whole expression of ys was this, right? So we have converted this part, so we just need to add 1 s squared plus twice s plus 5 there. So we just need to add plus 1 divided by s squared plus twice s plus 5. So this is going to be the whole ys. And so if you see these two denominators are the same, so if we take them common, twice s plus 5 times, if we take common, then it becomes 2/3 of s squared plus twice s plus 5, and there was a plus 1/3 of s squared plus twice s plus 2. All right, so that's the final expression of ys. This is the final expression, and I hope that you have understood the mathematical procedure. So this is like a subtype. So you have two denominator factors which are giving complex roots, and the first two expressions of both the factors are the same. Then the part that is the same, we assume it as z. Then it just turns into another simple case of a thumbs up method, and then we use the thumbs up method to find the unknowns a and b, and then we substitute the value of z and the value of a and b, and then we get the total expression of ys broken up in the partial fraction forms. I hope you have understood it. Now we get to the second type, and this is the most interesting one, right? So for the second type, I think you can actually guess what the second type is going to be. The first type, the first two expressions were the same. In the second type, they're not going to be the same. So what will you do then? Let's take up a question. All right, so let's assume that you have been given a problem like this and you were asked to solve it. Okay, so let's look at the denominator again. The main thing about partial fractions, which type are you going to approach it? The denominators are the main indicators of which type should you proceed with. Okay, so if we look at the denominators, let's see. Here we have s squared, and here we have s squared plus 9. So s squared is just a case of repeated roots, right? So this one won't be bothering us very much. We already know. But s squared plus 9, that's a different case. So s squared plus 9 leads to the value of s being plus minus 3i, where I is the imaginary number. Okay, so this one contains a complex root and this one contains repeated roots. We know the procedure for repeated roots already. What's the procedure for complex roots? Okay, I'm going to show it in two ways. The traditional way, which I'm going to show later, but the first way I'm going to show you is merging the thumbs up rule into this expression. Merging the thumbs up rule into this expression, because so far we have learned that the thumbs up rule is the easiest way you can break up a partial fraction math problem. Okay, so how do you break this up into a thumbs up rule? Okay, so first of all, we have found that the roots of s, the complex root of plus minus 3i. So we can easily say that s squared plus 9 can be written in this pattern, right? There is no objection whatsoever. So we can easily write this gentleman right here as something like this. The numerator stays the same. The denominator, however, it's going to change like this, right? So now if you look at it, these two parts are unique roots and linear roots. Actually not linear, but these two parts can be done with by the thumbs up method, and this one can be done with the repeated roots method. All right, so let's test it out. Enough blabbering about theory. All right, so we can break this up just like this. We can break this into these parts: a divided by s, b divided by s squared, c divided by s plus thrice I, and d divided by s minus thrice I. All right, so in the previous method, or in the traditional method, we would solve it like this. I'm not saying this is an unorthodox method. This is also a very popular method. This is not something new that I'm inventing, but it's just a method that is more underrated than the traditional one. All right. So we would write the problem like this in the old way, or in the way that I have learned when I was in school, that I would write it like that: a, b, and c s plus d divided by s squared plus 9. And then we would find some unique values. I mean, what are the unique values that we get in here? We only get s is equals to 0. And for that, we're going to get the value of b and nothing else. We have no other unique value. And for the other values like a and c and d, we would use the equating coefficients. All right, we'll delve into that a little bit later. But first, let's proceed with this one. All right, in this method, in order to find b, we're going to have to put s is equals to 0 for b. All right, putting s is equals to 0 in the left-hand side expression leads that 40 divided by thrice I times minus thrice I. So it's going to be 40 by 9. So that's the value of b. And in order to get the value of c, we're going to have to put s is equals to minus thrice I. So all right, this is the expression that becomes when we plug in s is equals to minus thrice I into the left side expression. How to solve it? It's not that complex to solve. We're just gonna switch our calculator into complex mode, and then we are going to plug in the values of minus thrice I manually into the calculator and let calculator do all the calculations. All right, so the result becomes 5 by 9 plus 25 by 27 I. And for the value of d, we're gonna have to plug in s is equals to thrice I. All right, you know what? We don't need to manually input s is equals to thrice I and manually type this whole expression in the calculator and try to solve it, because there is an advantage here. The value of c and the value of d are always going to be conjugates of one another. That's another beauty of this process, that you can actually say that the value of d is just that without calculating. If you want, you can verify it by calculating. All right, so these are the values of c and d. Okay, so we have found everything except a. All right, so in order to find the value of a, we're going to go back to the cover-up method, and we know that this is an identity, so this is valid for all values of s, and we have tried s equals to 0, minus 3i, plus 3i, and let's try s is equals to 1 on both sides of the equation, and then we're going to get the value of a. But before we do that, we need to furnish up this c and d side right here. How do we furnish that? Okay, let's see. So we have found the values of c and d. So the values, if we plug in the values into the partial fraction expression right here, it looks something like this. Okay, so we don't want to keep complex numbers into our whole expression, so we're going to have to transform it into this form right here. How will we transform it into this form? Do we just add these two fractions together and we're going to find this form automatically? All right, so first of all, if we add these two fractions, then denominator is going to be s plus thrice I times s minus thrice I, but we have already known that this is actually equals to s squared plus 9, right? So we can easily substitute these two with s squared plus 9. All right, and now what of the denominators? Okay, first of all, let's just look at these two expressions. All right. The coefficients of s, by multiplying which and which, we get the coefficient of s like this. 5 by 9, I mean, this whole expression is going to be multiplied with this one, right? So if we write it like this, 5 by 9 plus 25 by 27i times s minus thrice I. All right, and the second part is going to be multiplied by that. All right, so which expressions will get us the coefficient of s? Like this is going to be multiplied with s at some point. This is also going to be multiplied with s at some point. And if we look at the I part, this one, So this is going to be multiplied at s, and this is also going to be multiplied with s, but this one has a plus and this one has a minus. So these two expressions will get cancelled out. So we don't need to worry about the I and the s expressions. I hope you have got that. If you like, you can multiply these two and see that they actually cancel out. So we can find the coefficient of s by just multiplying these two. So what is going to happen here? So we're gonna get a 5 by 9s here and another 5 by 9s here. So we can say that the coefficient of s is going to be this, right? If we add these two, so there's going to be 2 times 5 by 9s plus. All right, so now about all the I segments or all the I expressions. Okay, just look at this little line here and you'll figure it all out. Minus 3i is going to get multiplied with 5 by 9, right? And here also plus 3i is going to get multiplied with 5 by 9. So as these two are conjugates, minus 3i multiplied by 5 by 9 plus 3i multiplied by 5 by 9. So it is common sense that these two will also cancel out. So we have established that all the I expressions get cancelled out. This one and this one gets cancelled out. 5 and thrice I, 5 by 9 and thrice I, and 5 by 9 plus thrice I, they also cancelled out. So we don't need to worry about the I expressions at all. We only need to worry about the real part and the imaginary I squared part, I squared expressions. So from where we get the I squared expressions from? This one will give us an I squared expression, and this one will give us an I squared expression. All right. So we have got 25 by 27 times negative thrice I. There is an I here. All right. Plus we get a negative 25 by 27 times I times thrice I. All right. So from what does this expression give us? What does this expression give us? Let's see. The I and I multiplied together, I squared is equals to minus 1. We all know that. We all know that, hopefully. So this is going to give us minus 1. There is also another extra negative here. So negative is going to be positive. So 25 by 27 times 3 plus there is also another negative here, and I squared is going to be negative 1. So negative is going to be positive. So this is also going to be 25 by 27 times 3. So this simply gives us 2 times 25 by 27 times 3. So we can actually plug in this constant right here, 25 by 27, 2 times 3. All right, so let's establish a rule that how do we get the coefficient of s and how do we get the coefficient constant part. So in order to get the coefficient of s, you need just to multiply these two and double it. You just need to multiply these two and double it. In order to get the constant part, you need to multiply all the imaginary parts and double it. So we have multiplied 25 by 27 with 3, and then we have doubled it. And if you don't want to establish any rule, you can just simplify the equation like that, and then from this equation you can figure out the rest, so that you don't have to be preoccupied with the rules in the examination itself. Okay, so the final expression becomes s squared plus 9, 10 by 9 times s plus 2550 by 27. So it's going to be 50 by 9, actually. 50 by 9. Okay, so this is s squared plus 9. All right, so you see, if we compare this form with the form of the traditional one, we can see that these two forms are exactly the same. We have found the coefficient of s and we have found the constant part. So, and we have found it quite easily just by using complex numbers. Okay, so we can write it. We can write the whole expression just like this by plugging in the value of all the numbers that we have got. We can say, all right, this is the expression, this is what the expression becomes, the resultant expression. So in order to find the value of a, let's plug in s is equals to 1 on both sides, and let's see what the equation becomes. So the left hand side becomes 6, which is A. This is going to be 40 by 9. This is going to be 10 by 9 plus 50 by 9 divided by 10. Okay, so from this, the value of A becomes, the value of A is 2, and that's our answer. We found the whole expression. So if we just plug in 2 into this expression right here, we're going to get our full form of partial fractions. Okay, so that's about it. I hope that you have understood this math right here. So this one is using complex numbers and using them to form a partial fraction. Okay, let's do another one and then we'll call it a day. So let's say we have another question like this. All right, so let's say we have an expression like this. So in the traditional way, we would have written that a divided by s minus 1 plus bs plus c divided by s squared plus 1. But in our method, we're going to use the complex number. If the denominator requires complex, if the denominator brings in complex roots into the family, then we're going to also take advantage of that. Why not? Okay, so s squared plus 1. If we check the roots of that, this is going to be plus minus I. So we can easily write this one as s plus I and s minus I, right? So we can easily say that the expression is not s minus 1 divided by s squared plus 1, rather it's like this. And with that, we can easily use the thumbs up rule to find and go to the answer, right? I don't think this is necessary anymore to go to the whole process again. Let's look at another example. This is going to be your homework, folks. And let's look at another example. All right, so this example, it's also pretty straightforward. It gives away the complex root bearing denominator right here. So for these two linear roots, thumbs up will be enough, right? We're going to use the thumbs up rule to determine the unknown coefficients. But for this one, we're going to have to use the complex roots method. We're going to have to use the complex roots method. Let's do this one. Okay, this one looks a little bit heavier and a bit scarier than the previous one. So let's say we write it up. All right, so the roots of this equation is a little bit weird and the denominators look a little bit weird, but no need to be scared of. We can defeat this thing. Okay, so in order to find the values of a and b, let's plug in s is equals to -2 and plug in s is equals to 3 for the values of a and b, and let's get it over with. All right, so the value for a is -1/25. And the value for b is going to be 3 divided by 50. Okay, and the value of c, we're going to have to input s is equals to -1 plus twice I into the left hand side expression. So this expression is going to become like this. All right, so we're not going to input the -1 plus twice I part into this equation right here, and you all know the reason already. All right, so the value for c, and we already know what the value of d is going to be. The value of d is going to be just the conjugate. Okay, so we have found our corresponding values of a, b, c, and d. Okay, so let's plug them in. First of all, before plugging them in, let's furnish the c and d part first. All right, so for the c and d part, we have found that, all right, so we need to add these two fractions together in order to get them in a standard form where there are no complex portions. So in order to do that, the denominator is going to become this, and the numerator, okay, so let's try to find the coefficients. We can actually take this thing common. So if we take this thing common, the coefficient of s plus 1, the coefficient of s plus 1 is going to be 18 by 25 gets multiplied with s plus 1 here, and 18 by 25 gets multiplied with s plus 1 there. So we can say that it's 2 times 18 divided by 25 times s plus 1. And for the imaginary part, we don't need to worry about the I portions. We need only worry about the I squared portion. So this is one I squared and this is another I squared. So these two are going to be the constant part. So 1 by 25 times 2. Okay, so that's our thing. Okay, so now we're gonna do that 2 times 18 divided by 25 s plus 2 times 18 by 25 plus 4 divided by 25 divided by s squared plus twice s plus 5. And that's our answer for the furnished part of the C and D. So this is the furnished part of C and D. So what we can do in the final part is that, so the whole expression is going to be the value of E is negative 1 by 25 times S plus 2. All right, so that's the answer. And I hope you have understood this method.